Hello friends, welcome to video series on geography. In my previous video I've explained about temperature distribution on Earth. In this video I should have explained about pressure systems and wind systems. But before we move on to pressure systems and wind systems, we need to understand certain basic concepts like adiabatic lapse rate and latent heat of condensation. These topics keep on appearing in our study of climatology from wind systems till tropical cyclones, so they are important concepts. And before we understand what is adiabatic lapse rate, let us study about few important physical phenomena. So first let us answer two questions. One, why a bubble of water rises from bottom to top in a pond or any other water body, and then why its size increases as it moves from bottom to top. First thing we need to know that as we move into deeper layers of the pond or any such water body, the pressure increases. As a result, the size of the bubble is small at the bottom layers as the pressure from all directions is greater. And due to this pressure, the size of the bubble is quite small. And as we move topwards from the bottom, the pressure usually falls. This is because of less amount of weight offered by upper layers. And hence the pressure on the water bubble decreases. As a result, the volume of the water bubble increases. So this is because of the decrease in ambient pressure which is acting on the bubble. And then why does the bubble move from top to bottom? So we know that at the bottom layers usually the pressure is greater. Let us consider this is P1. And then we move to a certain height, let us say till here, and let us call this pressure at this layer is P2. And we have seen that as we move from bottom to top, the pressure usually falls. That is, as we move upwards, the pressure is decreasing. So the pressure acting at this surface is much higher, and the pressure acting on the top surface is comparatively lower. So P1 is greater than P2. As a result, there is an extra force which is acting on the downward side or the bottom surface of the water bubble, and this force keeps on pushing the water bubble towards upper layers, and as it moves upwards, the pressure at the bottom layer of the bubble, that is here, is comparatively greater compared to the top layer. As a result, this pressure, additional pressure, gives rise to a rising movement of bubble, and this force is called as buoyant force. Usually the buoyant force is the one that keeps ships or any other floating thing which floats on water. So the buoyant force keeps them floating on the surface. So this same buoyant force pushes the bubble upwards. As a result, the bubble moves from bottom to top. So we have seen the increase in volume and also the movement of bubble from bottom to top. And now let us see how it is related to adiabatic lapse rate. Let us consider a parcel of air. A parcel of air is simply means that an air which has more or less a homogeneous temperature region, that is the temperature of whole of this parcel of air is quite same, and it also has the same physical and chemical properties, that is it has the same composition and other properties, hence we call it a parcel of air. And we know that air molecules are separated by a distance, and in liquids this distance decreases, and in solids the molecules are very much closer. So when we supply certain amount of heat to the solid molecules, they gain some energy to overcome the attractive force between the molecules, and when certain amount of attractive force is overcome, then the distance between the molecules increases and the solid turns into liquid. And when we apply more amount of heat, then this liquid will get converted into gas. So we know that this is what we see, that when we increase temperature of a system. So when we increase the temperature of a system, usually the volume falls because of greater increase in size due to greater space between molecules. So let us see this parcel of air which is getting heated by sun's insolation or sun's radiation. So when it absorbs certain amount of heat, the molecules move farther away, increasing in volume. So the original size increases due to reception of heat or due to absorption of heat. And when the parcel's size increases, it is usually at a lower pressure compared to the surrounding regions. So we have seen how a water bubble moves from top to bottom when there is lesser pressure compared to the outer system. Likewise, in the other case as well, also a parcel of air moves from bottom to top when there is pressure which is lower than the surrounding environment. So let us consider that this is a parcel of air which is at a pressure of 10 Pascal, or we can call, usually Pascal is a unit of pressure, not so important what it is. So, and let us consider the surrounding air at this layer which is at a pressure of 12 Pascal, or let us consider both being equal at 12 Pascal. And when there is certain amount of heat applied to this parcel of air, then its pressure reduces. So its pressure falls from 12 to 10 Pascal. As a result, it is at comparatively lower pressure. So there is extra buoyant force which is acting on this air parcel. As a result, this air parcel alone moves upwards, or it is uplifted. So this upliftment is associated with some very important phenomena like precipitation, etc. So we'll see that how it happens. So in this example, we can see how a smaller parcel of air after certain heat reception decreases in volume, and increases in volume, and this increase in volume results in lesser amount of pressure than the surrounding regions, and this fall in pressure uplifts this air parcel further upwards, and as it moves upwards, the water vapor condenses. So before understanding what is this condensation and all, let us see what is lapse rate. For studying lapse rate, we need to know about Earth's atmosphere. In the previous video, I've explained about Earth's atmosphere. We have seen this is Earth, and the first, or the layer that is surrounding the Earth's surface, is called as troposphere. And we know that in troposphere, the pressure falls as we move from bottom to top, that is from surface to the upper layers of troposphere. So this fall in pressure is very important because when there is less amount of pressure acting on a system, its temperature is usually low. For this, let us see an equation, or which is stated by gas law, which says that pressure is directly proportional to temperature, which are both inversely proportional to volume. So what does this mean? When pressure of a system increases, when we keep volume constant, then temperature also increases. And a vice versa phenomena, where pressure falls, the temperature also falls, considering that volume is a constant. And likewise, when temperature increases, pressure increases when volume is kept constant, and in the other case, when temperature falls, pressure also falls when volume is kept constant. So this is what gas law states. So we'll apply the same principle here. So when a parcel of air is moving upwards, what is happening? The pressure on the parcel of air is falling. As a result, its volume is increasing. So this is what we have seen, where pressure is and temperature are inversely proportional to volume. So when pressure falls, volume increases. And when we come to Earth's atmosphere, the pressure at the outer layers is comparatively lower, whereas the pressure at the surface is much greater. This greater pressure creates greater amount of temperature at the surface, whereas the temperature at the outer layers of troposphere is comparatively small. So this difference in temperature is mainly due to variations in pressure acting at each of the surfaces. And other than this, we know that Earth has a blanket of air, and this air is denser in the troposphere, and it contains various important greenhouse gases like carbon dioxide, water vapor, methane, etc. So when there is a sun's ray which is coming towards this atmosphere becomes completely or partially transparent for this sun's rays. And when this sun's rays hit the Earth, it is absorbed by Earth, and this absorbed energy is released in the form of terrestrial radiation or infrared radiation, that is heat. And when this heat is transferred back into space, there are certain greenhouse gases like water vapor, etc., which completely absorb or partially or greatly absorb this heat. As a result, the temperature of the atmosphere increases. And we know that we have greater amount of water vapor content at the surface, whereas the water vapor at the top layers is comparatively lower. As a result, the absorption is greater at the lower layers compared to the topper layers, and hence the temperature at the very near surface of the Earth is much greater compared to the topper layers. So there is great temperature at the surface, whereas at the upper layers of troposphere the temperature usually falls, and this differences in temperature is nothing but lapse rate. So let us consider this is Earth. As we move certain distance away from the earth, usually the temperature falls. It is called as lapse rate, and the lapse rate is about 6.5 degrees Celsius for every 1 kilometer rise in height. So as we move 1 kilometer away from earth, the temperature fall is about 6.5 degrees Celsius. So this decrease in temperature is due to the lesser amount of greenhouse gases in the upper layers, as well as the distance greater, the pressure at which is quite low at the upper layers compared to at the surface. So there are two factors, one is pressure, other one is greenhouse gases. So both these things result in this concept called as lapse rate. So we have seen this, for every 1 kilometer increase in height, the temperature falls by 6.5 degrees Celsius. So this is an average for all of earth, so this is not same at every region. It usually varies from region to region, but on an average we take that it is about 6.5 degrees Celsius. So this is what is lapse rate. And before we study about adiabatic lapse rate and then wet adiabatic lapse rate, dry adiabatic lapse rate, etc., first we need to look at a concept called as latent heat. So for studying latent heat, first we need to answer a few very important questions. They are just physical phenomena. One is, why do we feel cold when there is too much sweating, that is during higher temperatures? And then why does a matki or a earthen pot cools water during summers or hot temperatures? To understand this, let us understand the phenomena between both these things. For that we need to know first the concept of latent heat. So first let's study that. Let us assume that there is certain amount of heat which is supplied to a system. The system, let us consider it's a boiling pot of water. Let us consider this is water which is supplied with certain amount of heat. And then when we supply heat at a certain level, the liquid in the water converts into gas. So gas flows away. So during this process there is something called as latent heat which is absorbed by the system. Latent heat is nothing but the heat which is absorbed or released during change of state. Change of state is nothing but when a substance turns from liquid to gas, or gas to liquid, or liquid to solid, or solid to liquid. All these are nothing but change in state of matter or change in phase. So let us see what happens. This is heat we are applying, and this is temperature raised in the system. So as we apply heat at the initial stages, the temperature of the system increases, as we can see in this graph. But at a certain point, the temperature remains constant while we are supplying heat. So the heat we are supplying during this phase is utilized by the system to change the phase of the system. For example, here the change is from solid to liquid, and this change occurs during this temperature range. And this temperature range where there is no increase in temperature of the system but there is only phase change is called as latent heat of, usually it is called as latent heat of freezing or whatever it is when there is melting or freezing. For this example, it is called as latent heat of fusion, where solid is converted into liquid. And in another case, let us see in the next phase, that is when liquid is converting into gas. And here again, after the phase change from solid to liquid, we have increase in temperature of the system with the supply of heat. But at this stage, though we supply heat, there is no increase in temperature. This is because there is change of a state here, where all the heat supplied is utilized by the medium to change its phase or to get converted from liquid to gas. So this amount of energy which we have supplied, and then the same energy which is utilized in change of state, is called as latent heat, and here it is called as latent heat of vaporization. So what is happening during latent heat of vaporization? The heat we are supplying is consumed by the system. Likewise, when a gas converts into liquid, it releases the exact amount of heat into the system. So here it is called as latent heat of condensation. So latent heat of vaporization is the heat absorbed, whereas latent heat of condensation is the heat which is released. So this latent heat of condensation is very important for us to understand why sweat decreases the temperature of the body, as well as why water in earthen pot is so cold. For this, let us consider a body, and when there is greater temperature in the external environment, usually our sweat glands releases sweat. So this is sweat and this sweat simply absorbs the heat in the body. So this is nothing but latent heat of vaporization, which is being absorbed by sweat. And by absorbing this heat, the sweat gets converted from liquid state to gaseous state and it evaporates. So when it is evaporating, what it is doing is it is simply absorbing the heat of the body in the form of latent heat of vaporization. So when there is heat absorption from the body, it is nothing but the heat is decreasing on the body surface, and hence we feel cold. So now let us consider the example of earthen pot. Earthen pot has small pores on it. So when we fill it with water, there is certain amount of water which is oozing out of these pores. And when there is certain droplets that are present on the surface of the earthen pot, and this water droplets convert from liquid to gaseous state, and during this change in state there is latent heat of vaporization which is being absorbed from the earthen pot. And this absorption from the earthen pot simply means that the temperature of the earthen pot surface is decreasing, and hence the earthen pot simply becomes much colder, and as water inside is in contact with this earthen pot, it also becomes cooler. So this is the principle behind the cooling of water in earthen pot, as well as the feeling of coolness when we sweat. So this is nothing but latent heat. So when it is supplied, it is called as latent heat of vaporization, and when it is released, it is called as latent heat of condensation. In our study of climatology, latent heat of condensation is a very important concept. So this will help us in understanding both precipitation and cyclonic systems. For that, we'll see that later in our future videos. Now let us see about adiabatic lapse rate. Let us come back to adiabatic lapse rate. We have seen that adiabatic lapse rate is nothing but fall in temperature as we move upwards. It is about 6.5 degrees Celsius for every 1 kilometer increase in height. And then there is a very normal adiabatic lapse rate, that is we consider in practical terms in general situations. It is called as adiabatic lapse rate. So adiabatic lapse rate is nothing but the lapse rate in normal conditions. So in normal conditions we have certain amount of moisture in air, as well as there is other certain features like the component of gases, composition, etc., which are all very similar or typical. And in such cases, the adiabatic lapse rate is usually 6.5 degrees Celsius, and it is called as environmental lapse rate or adiabatic lapse rate. And there is one more concept called as wet adiabatic lapse rate, which is also called as saturated adiabatic lapse rate. So wet adiabatic lapse rate is comparatively much smaller compared to adiabatic lapse rate. Let us see why this happens. Let us consider a parcel of air which has water vapor content which is above normal. So let us consider that a parcel of air has 1 kg of water vapor during normal times, and let us consider a new parcel which has 2 kg of water vapor, and when this water vapor is heated, what happens? It rises because of increase in temperature, and during this raising it reaches a certain level of atmosphere where the temperature falls due to lapse rate, and at this very level the temperature due to adiabatic lapse rate falls. It is about 6.5 degrees Celsius for every increase in 1 kilometer, and at certain height the temperature becomes so cold that the water vapor starts condensing. So when water vapor starts condensing, it forms a liquid. It gets converted from water vapor state or gaseous state to a liquid state, and at this stage the heat is released into the system, which is called as latent heat of condensation. So we see that there is fall in a temperature of 6.5 degrees Celsius, and due to some certain amount of temperature, and due to condensation there is release of temperature into the system. Let us assume that it is about 2 degrees Celsius. So the effective fall in temperature will be 6.5 minus 2, because this is added to the system. The 2 degrees Celsius is added to the system. So the effective fall in temperature will be 4 degrees Celsius. Though the normal lapse rate is 6.5 degrees Celsius, but when we have greater amount of water vapor, usually the lapse rate becomes much lesser than adiabatic lapse rate. It will be around 4, 5 or anything less than 6.5, and this is what we call as wet adiabatic lapse rate. So what does this signify? It simply says that when there is greater amount of moisture in the water in the air parcel, then the fall in temperature is comparatively lesser than the normal fall in temperature. That is, it will be lesser than this 6.5 degrees Celsius. And let us consider the exact opposite situation in dry adiabatic lapse rate. Let us imagine that a parcel of air has 0.5 kg of water vapor, whereas in normal air we have about 1 kg of water vapor. And again, when there is heat supplied, this air gets uplifted, and during the upliftment process the water vapor gets condensed, and when it gets condensed there is liberation of latent heat of condensation or release of latent heat of condensation. But we have seen that in dry air the water vapor content is much lower, that is it is below normal. As a result, the latent heat of condensation which is being released during this stage is much lesser than compared to the release of latent heat of condensation during normal phase. As a result, this heat released is much lower, and hence the fall in temperature will be much greater. So let us assume that this is 6.5 degrees Celsius, that is the normal fall in temperature. And in normal fall there is latent heat of condensation which is being released. As a result, the temperature the temperature fall is usually small. But when there is much lesser presence of water vapor, the heat supply to the system will be much smaller. As a result, the adiabatic lapse rate will be much higher than the present system. So it would be anything above 6.5. So usually the dry adiabatic lapse rate is near to 10 degrees Celsius. So we can see that for every 1 degree increase in temperature, the dry air will have an adiabatic lapse rate of 10 degrees Celsius, which is much greater than 6.5 degrees Celsius. So what all these things state us? Let us see this. For this, we need to see what is absolute stability, conditional stability and absolute instability. And before we understand this, we have seen that when there is greater amount of water vapor, there is greater amount of condensation, and hence there are greater chances of rainfall. And when there is an environment where the chances of rainfall is higher, and such a state is called as instability or unstable conditions. And in other case, where we have certain amount of moisture like in the normal times, but still this moisture is not sufficient enough to form significant amount of precipitation, so this condition is called as conditional stability. So it can rain or it may not rain. In other case, when the moisture is too low, that is in the case of dry adiabatic lapse rate, when the moisture is too low, in such a scenario, the formation of the condensation of water vapor is also very low, and as a result the chances of precipitation is very low, and such a state is associated with absolute stability. So if you look at this small equations or whatever it is, so we have adiabatic lapse rate, which is a normal state, and then we have wet adiabatic lapse rate, and then dry adiabatic lapse rate. So in absolute stability, the adiabatic lapse rate is much smaller than both WALR and DALR. So this simply signifies that the amount of moisture content in the air is much lower. So we have seen what is wet adiabatic lapse rate and what is dry adiabatic lapse rate. So compare it here. So if wet adiabatic lapse rate and dry adiabatic lapse rate are lesser than 6.5, are greater than 6.5, in such a case the temperature or the lapse rate would be much greater, but it also signifies that the water vapor content in the atmosphere is quite low, hence it is associated with absolute stability. When we come to conditional stability, here adiabatic lapse rate lies between dry adiabatic lapse rate and wet adiabatic lapse rate. It simply means that there is a certain amount of moisture in the water vapor which is very close to that in the normal condition, and hence the situation is that it may be stable or it may get unstable, but it is still uncertain, hence we take it as conditional stability. So we need not go deeper into understanding this. If you have understood wet adiabatic and dry adiabatic, then these concepts are very simple. I will not go in very depth explanation because it takes a lot of time. And again, we have absolute instability. Here we see that adiabatic lapse rate is much greater than wet adiabatic and dry adiabatic. This simply means that the current parcel of air has greater amount of moisture, and due to greater amount of moisture, what happens is there is greater chances of precipitation, and hence it is associated with absolute instability. So don't worry much about these things, just remember these conditions, that's enough. They are very unlikely to come in the examination, but these are just basics which we need to know to study future concepts like precipitation and tropical cyclones, temperate cyclones, etc. So before winding up the video, let us see at few questions. These are questions asked in previous prelims examination. The amount of moisture in the atmosphere is related to latitude. This is assertion. And the reason for this is the capacity to hold moisture in the form of water vapor is related to temperature. So to answer this question, first let us talk a little about temperature and moisture. Let us imagine an ocean surface which has great amount of water, and then there is certain amount of temperature which is received by this ocean. And when there is great temperatures, then the evaporation will be considerable, that is the greater amount of evaporation, and hence the water vapor content in the air will be greater, that is the moisture content will be much greater. And there is another situation where there is lower temperature, where evaporation becomes much lower. So when there is little evaporation, the moisture or water vapor content in the atmosphere will also be lower. So what does this say? It simply says that temperature and moisture are highly interrelated, and when there is greater temperature, the amount of moisture in the atmosphere is higher. So this point is correct. So let us look at the first point. The amount of moisture in the atmosphere is related to latitude. Let us see how these points are related. So let us consider this is Earth. We know that insolation is maximum at the equator. So when insolation is maximum at the equator, the temperature also is maximum, and hence the evaporation will be much greater at the equator. And as we move towards poles, the insolation gets reduces because of the shape of the Earth, and hence the amount of temperature received is lower, and hence the evaporation is also lower. So when evaporation is lower, we see that there is lesser chances of condensation and precipitation. That's another concept. But if you see the point, the amount of moisture in the atmosphere is related to latitude. Hence, yes, it is related to latitude. How? We have seen this. Evaporation is greater at the equator and it reduces with latitude. This is because of change in temperature. So these points are self-explanatory, and you can see one point is related to another. That is, increase in latitude results in increase in temperature, and increase in temperature results in increase in moisture, that is moisture or water vapor. So this point, that is assertion, is correct. Both reason is also correct, and the reason is the correct explanation of the assertion. So the answer is A. Next question. Normally the temperature decreases with the increase in height from Earth's surface because the atmosphere can be heated upwards only from the Earth's surface. There is more moisture in the upper atmosphere. The air is less dense in the upper atmosphere, and these are the options. So let us consider the easiest option of all this. That is the third option. The air is less dense in the upper atmosphere. We have studied in atmosphere that the troposphere has certain amount of pressure, air pressure, where the lower troposphere is at greater pressures, whereas the upper troposphere is at lesser pressures. This is nothing but air is less dense as we move upwards. This is what the point says. The air is less dense in the upper atmosphere. So as we move upwards into the atmosphere, the air is less dense, as well as pressure is also comparatively lower. There is more moisture in the upper atmosphere, and again we have seen that in the previous video that the moisture content in the atmosphere is greater at the surfaces of the Earth, whereas as we move upwards, the moisture falls. So the point 2 is wrong, whereas point 3 is correct. And then coming to the third point, so let us look at the elimination process. So we have the third point absolutely correct. So the answer would be between 3, that is B, C and D. One is completely wrong. So if you take the second point, we have seen that it is absolutely wrong. So option B will be wrong as it has point 2, and then option D will also be wrong. So here we have directly got the answer without even looking at the first option by simply eliminating the wrong ones. So the answer will be C. So but still we should look at for better understanding the point 1. The atmosphere can be heated upwards only from the Earth's surface. So in the beginning of the video, I've explained about how greenhouse gases influence the temperature of the atmosphere. We have seen that the incoming rays directly enter the atmosphere without much being influenced by the constraints of atmosphere, whereas the outgoing radiation, that is terrestrial radiation, is completely or partially absorbed by atmosphere and various other gases. So the absorption of terrestrial radiation is much greater. As a result, the atmosphere can be heated upwards only from the Earth's surface. So this point is also correct. So friends, this is the end of the video, and if you liked my video, please give a like, thumbs up on the video section, and then please share my videos so that it reaches more people who are in desperate need of coaching for geography, and give your feedback, give your opinion about the whole series. And then please subscribe to my channel so that you'll be receiving updates instantly. And thanks for watching, and keep visiting my YouTube channel. I'll be posting more videos. Thanks guys.